Passing clinical board exams depends on your ability to parse data in real time. You must take a complex clinical abstract, extract the signal from the noise, and instantly evaluate the integrity of the data. Today, we are testing that exact skill. We are looking at a recent study asking a highly practical question. Does early structured lactation counseling actually improve exclusive breastfeeding rates at 6 weeks postpartum? We will treat this study as a mock board exam prompt. We are going to rapidly parse the methodology, identify the study design, and interpret the statistical significance of the findings under simulated exam conditions. Our raw data source is an abstract tracking 240 postpartum mothers who delivered at a tertiary care hospital. Half of these mothers received at least one structured lactation counseling session within 24 hours of delivery. The other half received standard routine care. The researchers then followed both groups to measure one specific primary outcome: the proportion of mothers exclusively breastfeeding at the 6-week mark. Mastering this appraisal process allows you to separate rigorous evidence from statistical noise. It is the primary tool used to evaluate whether a clinical intervention actually merits a place in your practice. Let's open the first exam block. To interpret any results, we first have to direct our attention to the methodology section to determine how the researchers structured their observation. Question 1. What is the most appropriate description of the study design used? Your standard options are a randomized controlled trial, a cross-sectional study, a prospective cohort study, or a case control study. First, scan for the word randomized. It is absent. Furthermore, the abstract explicitly refers to this as an observational study. We can immediately eliminate the randomized controlled trial. This diagram shows the flow of time described in the methodology. The subjects are grouped by their current exposure status, counseling versus routine care, and the study tracks them flowing forward in time to a future outcome at 6 weeks. Tracking a specific group forward in time from a known exposure to a subsequent outcome is the defining mechanical characteristic of a prospective cohort study. The text confirms this by stating the subjects were classified based on exposure and then followed up. This locks in prospective cohort study as the correct answer. Identifying the temporal direction of the study is a mandatory first step. It dictates exactly which statistical tools the researchers are permitted to use. Before calculating any statistics, cohort studies require rigorous baseline grouping. Let's look at an advanced question based on a single sentence in the abstract's exclusion criteria. Why did the researchers explicitly exclude mothers with medical contraindications to breastfeeding? The correct clinical answer is C, to prevent confounding by indication. Confounding by indication occurs when a patient's underlying condition dictates both their treatment group and their outcome, skewing the data. Consider what happens if we leave these contraindicated mothers in the study. Because they have medical issues preventing breastfeeding, they are highly likely to end up in the routine care group rather than actively seeking lactation counseling. These specific mothers have a 0% probability of achieving the primary outcome of exclusive breastfeeding, regardless of the care they receive. Leaving them in the unexposed group would artificially depress that group's success rate. Removing this population entirely cleans the dataset. It isolates the true effect of the structured counseling on mothers who actually have the physiological capacity to breastfeed. Robust cohort studies must strictly clean their baseline populations. Without these exclusion criteria, skewed baseline risks mask themselves as treatment effects. Now that we have established a clean prospective cohort, we can evaluate the statistical results. Question 2 asks, which measure of association is most appropriate for the primary outcome? Our choices are odds ratio, relative risk, hazard ratio, or correlation coefficient. We can rule out the odds ratio. That metric is primarily reserved for retrospective case control studies, where the researchers look backward and the baseline incidence of a condition is unknown. We also rule out the hazard ratio. This study measures a simple binary outcome at a fixed point in time, 6 weeks, rather than tracking time-to-event survival data over a continuous sliding period. This equation visualizes the correct answer, relative risk. Because a prospective cohort design tracks all subjects from the very beginning, researchers know the exact size of the population and can calculate true incidence. We divide the incidence of the outcome in the exposed group, 65%, by the incidence in the unexposed group, 45%. This yields the reported relative risk of 1.44. Verifying that the researchers matched the study design to the correct statistical tool, cohort studies to relative risk, is a foundational check of the paper's mathematical validity. We have a calculated relative risk of 1.44, paired in the abstract with a 95% confidence interval stretching from 1.12 to 1.85. Question 3 asks, how should we interpret these specific numbers clinically? First, we look at the point estimate. An RR of 1.44 tells us mothers in the counseling group are 44% more likely to exclusively breastfeed than those receiving routine care. This is a forest plot framework. We use it to determine if that 44% increase is statistically significant or just a product of random chance. The vertical dotted line at 1.0 represents the line of no effect, where both groups have identical outcomes. We plot our point estimate, 1.44, to the right of the line. Then we map the 95% confidence interval, drawing arrow bars out to 1.12 on the low end and 1.85 on the high end. Notice the placement of the entire horizontal bar. It sits completely to the right of the 1.0 line. It never touches it, and it never crosses it. Because the lowest possible mathematical value in our interval, 1.12, is still greater than 1.0, we can confidently reject the null hypothesis. The association is statistically significant. Take a look at this new forest plot. What if the researchers reported a higher point estimate, an RR of 1.50, but the confidence interval was much wider, stretching from 0.95 to 2.10? Because that interval crosses the line of no effect, the true value could be exactly 1.0. The finding becomes mathematically indistinguishable from random chance, rendering the high point estimate entirely irrelevant. Let's shift our focus to the secondary visual data provided in the abstract. We need to verify the raw outcomes and check for methodological flaws that could invalidate our relative risk calculation. This vertical bar chart compares the raw outcome difference. We see exclusive breastfeeding rates hit 65% in the counseling group and 45% in the routine care group. This visual perfectly aligns with the calculated relative risk, confirming definitive higher success in the exposed group. This line graph tracks the study's follow-up completion rate to help us assess for attrition bias. Over the 6-week period, both lines decline in tandem. The loss to follow-up is exactly 10% in both groups. Because the attrition is perfectly symmetrical, the risk of differential attrition bias skewing the results in favor of one group over the other is minimized. Finally, question 5 asks, given these findings, what is the primary limitation of this study design? The correct answer is residual confounding. Because this is an observational study and patients were not randomly assigned to groups, we cannot definitively prove the counseling caused the increase. It is entirely possible that highly motivated mothers simply opted for both the counseling and the exclusive breastfeeding. Our final appraisal, this is a structurally sound prospective cohort study. It demonstrates a statistically significant positive association between early counseling and breastfeeding outcomes, but it remains limited by its observational nature and the potential for residual confounding. For your board prep, rely on this exact framework. Identify the temporal direction first, match the statistical measure to that specific design, verify confidence intervals against the line of no effect, and relentlessly hunt for baseline confounding. True clinical expertise relies on knowing exactly how the data was built, what it can mathematically prove, and where its structural weaknesses lie.